my pleasure to introduce Professor Erik Paemurru. Yeah, so here we talk about birational geometry of sextic double solids with compounding and singularity.
Hello. Thank you for inviting me to speak. So, yeah, I'll talk about birational geometry of these objects. So we'll start a bit more generally. So I'll use the term Mori-Fano for variety. To me, it means that just a Mori fiber space, which is a Fano variety over a point. So this means it's a Fano variety, and it has some conditions on the singularities, namely very mild singularities, terminal singularities. It's ℚ-factorial. That means every an integer, positive integer multiple of every weight divisor is Cartier, and its Picard number is 1. So these are the minimality conditions that appear in the minimal model program. And I want to consider what happens with these Mori fiber space Fano varieties. So if we run the minimal model program on some variety, then the endpoint, if it's unirational, then the endpoint is a Mori fiber space. And now if the endpoint is a Fano variety, which is a Mori fiber space, a Mori Fano variety, then we can ask, is this the only Mori fiber space in its birational class? So as we know, MMP can end in different outputs in different Mori fibrations. And we say the Mori Fano variety is birationally rigid if it's the only Mori fiber space in its birational class. So I'll say that this is some very unique or very strong property. For example, it implies that it's non-rational, the variety. And yeah, so for the objects that I study, sextic double solids, it's known that if they're smooth, then they are birationally rigid. And this appears also for some other varieties where if you know that it's smooth, then you know that it's birationally rigid. In terms of deformations, smooth can be thought of as the general case. And if you add singularities, then you make it somehow more special. You add some conditions on the variety. So we'll see what happens. So I will look at sextic double solids. This means these are double covers P3, and they're branched along a sextic surface. How I look at them is that they are a variety that's given by a weighted degree 6 equation in weighted projective space. So here, the weighted projective space variables I choose as x, y, z, t, w, where the first 4 x, y, z, t have weight 1 and w has weight 3. So this equation w squared equals f6. That's a quasi-homogeneous of weight 6, weighted homogeneous of weight 6. And yeah, F6 defines this branching surface. And these are the sextic double solids. So what we know from before is that a smooth sextic double solid is superrigid. That means it's the only Mori fiber space in its birational class, and also its birational automorphisms and usual automorphisms coincide. So it has been studied before. What happens if we add ordinary double points? So ordinary double points, these are the simplest kind of singularities. So an ordinary double point is local analytically given by xy plus zt. Let's see. I'm not sure if people can see this part, but yeah. And people also studied if we add more than one ordinary double point. So as long as the variety stays ℚ-factorial and you add ordinary double points, it still stays super rigid. So that's adding finitely many ordinary double points. So now this ordinary double point case is covered. We've looked at this. But there are other terminal singularities in the Mori category. I'll talk about these next. And yeah, throughout the talk, if you have questions, you can ask people in the audience or in the Zoom can also ask. I can see, hopefully I can see the questions in the chat. Okay. So the terminal singularities. So the simplest kind that follows the next simplest after ordinary double points is called an isolated compound AN singularity. And I will denote it CAN. So this means if you take a general section through the point, it's a Duval AN singularity. Let's say, do I have a description? I'll write on the board, and this board should be visible also for the audience. So AN Duval singularity is xy plus another pen. Right. Right. Okay. Let's see. I'll see how this goes. And then I can reshare. Okay, yeah. So this is reminding this Duval singularity AN. Okay. Now I'll go back. So this is, I click here. Yeah. Okay. Okay. So, and this singularity description, that's local analytic. We know already from the 80s that these isolated compound AM singularities, they are terminal. So these are the class of singularities we use in Mori theory. The simplest class where minimal model program works. So in what follows, I'll define the weight of a power series. So in general, we'll have some weights later for the variables. Right now, we'll have weights 1 for each variable. So if we write the polynomial or power series as a sum or infinite series of its homogeneous parts fi, then weight is just the degree of the least degree homogeneous part. So for example, weight of x squared plus x to the power of 6 is equal to 2. Okay. And from the description of Duval singularity I gave earlier, it's not difficult to show. In fact, it follows immediately that a CAN singularity is given by xy times x2 plus h, where the weight of h is n+1 here. So I studied these on Sextic double solids. The first thing I did was show that a Sextic double solid can only have CAN singularities where n is at most 8. And then for every n at most 8, a general Sextic double solid is smooth outside this point, this CAN point. And the very general one to the CAN singularity is a Mori fiber space. There's one exception family where it's not the Mori fiber space, where it's not ℚ-factorial, but yeah, a small point. So this is the preliminary step before we can study birational rigidity or birational maps between these Sextic double solids and something else. We have to see that there exists some Mori Fano Sextic double solids with these CAN singularities. See, yeah. So the way I proved it, so before people had done was use some Roth arguments to get some bound on this n. What's the highest n possible for a CAN singularity for some other families, for some other varieties, but here this Roth bound was not precise, and it was not so easy to get the precise bound. So the only way I could do it is actually parameterize all of these families completely. But yeah, getting bounds on the most singular variety or the most special variety is not so easy. So we'll see that if we have a point which is of type CA1, so a general CA1 singularity is just an ordinary double point, xy plus zt. And in this case, the parameter space is 77 dimensional. So that just means that in this form, W squared equals F6. F6 has lots of complex coefficients, which we can choose. And we'll get the 77 dimensional family. And here, one point is for CA7, we'll have 4 families. Okay, and how did I do this? So I look at the first, yeah, what is a CAN singularity? It's local analytically, it's x1, x2 plus h. And the point is a CAN singularity if and only if this h has multiplicity n+1. The first thing I would do is move the point to a convenient place. So I choose the point to be yeah, the point would be 1, 0, 0, 0, 0. So that point would have coordinates. X coordinate is non-zero, and the other coordinates are 0. Okay. And then, yeah, we have this condition that the weight of h, after I put it into this form, has to be at least n+1. In other words, for all of the previous homogeneous parts, they have to be 0. So what I'll do is I can express this h in terms of the original equation of x. So there's an algorithm how to put this h, how to put the starting from this W squared equals F6. I write it out. I write out all of the coefficients, a times x to the 6 plus b times x to the 5y, and so on. And in terms of all of these coefficients, a1, a2, etc., I'll describe H, the homogeneous parts of H. So these depend on the coefficients of F. And these conditions that H2 is 0, H3 is 0, etc. These are, every step we have some relations among the coefficients of F. So we'll have a bunch of conditions. So it's like a system of equations. Let's see. If we look at the dimensions, we start from 77, we go to 74, 70, 65, 59. We see that it's a sequence. The difference at first is -3, going to 74, then it's -4, -5, -6, etc. This is because the polynomial in two variables that's homogeneous of degree 3, of degree 2 that has 3 coefficients. If it's homogeneous of degree 3, it has 4 coefficients. We have to put them all 0. We get 4 conditions, and these are independent conditions. It's not clear a priori, but these are independent. But these will be. And to prove that it's smooth outside of that point, or that it's ℚ-factorial and Picard number 1, we use some dimension counting arguments. Okay. Yeah. Before this. Yeah. If you have any questions, you can ask.
Are you saying that there cannot be any, I don't know, isolated singularity of type C89?
Exactly.
And
That,
that's because by dimension counting, I mean, there's like the parameter space.
yeah.
Dimension is like, I don't know, there's no dimension.
Right. So if we add this condition that the homogeneous degree 9 part is 0, that's how we would find CA9 singularities there. If we add this condition H9 is 0, then if we solve this, we'll see that some of these conditions, it's not algebraically independent anymore. It's possible, like you can put a CA9 singularity on the Sextic double solid, but due to some dependence of these conditions, it won't be isolated. You'll have a curve of singularities through that point. Or what else could there be? It will be let's see. I think it's the yeah, it'll have some curve of singularities too. I think I'll talk about it. Yeah, that yeah, if we look at non-isolated ones, then the equations get too difficult to solve. I mean, in general, solving the equations is very hard because it's a system of equations. I don't know, let's say system of 30 equations in, I don't know, 77 variables, non-linear. It's not so easy to solve. It took me months to come up with something, or years, or to come up with a way to how to solve this. Yeah, years actually. So for the higher ones, we can't solve it completely. At least I couldn't. We can't parameterize it, the non-isolated singularities, but I constructed some examples with the CA11. And one thing I looked at is how many CAN singularities we can put there. And one easy bound we can get, which is not precise, is that local Milnor number of an isolated CAN singularity is at least n squared. And from a book we can read up and show that the total Milnor number is up to 104. So this part is known. So this quickly gives that it has up to one CA8 singularity or up to two CA7 singularities, etc., or up to 104 ordinary double points. But this is not precise, as we already know that a sextic double solid can have up to 65 singular points, up to 65 ordinary double points. So just to try to make this bound a bit sharper, I was thinking maybe this sparse sextic with 65 ordinary double points, maybe it's the most singular one in terms of the global Milnor number or global Divisorial number or some invariant. Maybe that's the most singular one. But it turns out that it's not, that you can get some more singular ones with some, if you add some CAN singularities. This is actually not new. That later I read that there's different techniques to get sextic double solids with high global Milnor number and high global Divisorial number. So yeah, classifying these very singular objects turns out to be very difficult. Yeah.
What do you mean by total Milnor number?
Right. I'll use the board now. I'll put the stop share. Okay. So I'll write here. So if we have a singularity given by f, so if we have a singularity at the origin given by f, then local Milnor number is given by, we take the C algebra of convergent power series and we take the quotient by the ideal given by f. So this defines a finite dimensional what's it called, vector space, and we can take the dimension over C. Jacobian, yeah, of course. Yeah. So, and the global one, that means you add up the local ones. So if you have some variety x, then the global one would be the sum of the local ones. So x p. Yeah. So a smooth point has local Milnor number 0. So this makes sense. So this is the sum of the local Milnor numbers of the singular points.
And then how can you bound this global Milnor number? So I mean, you claim that this global number is less than.
All right. How do I bound the global Milnor number? So this was through some Betty number argument that that was that there's some list of invariants for these sextic double solids, and just using some known topological invariants. Yeah.
Then it is kind of bound. Bound is defined by some Betty Kawakitas multiples for every Fano variety?
Yeah, there's it's from this book by oh, I don't remember the title. Fano 5 by who is this by? Sextic. Yeah. But they give some such invariants for the Fano varieties for yeah. Thank you for the question. Okay. Let's see. So yeah. So this was constructing these, trying what if we can add other CAN singularities other than isolated ones. So now we'll go back to isolated CAN singularities. We have this parameter space. So now we can work with this one. So, and the main theorem that I have is that a general Mori fiber space Sextic double solid that has a CAN singularity where n is at least 4 is birationally non-rigid. That means it's not unique anymore in its birational class. So yeah, before we saw that a general one is a general Sextic double solid is a Mori fiber space except for one family, and now we'll construct one variety that's birational to it. That's a Mori fiber space. And this birational map we construct through the Sarkisov program, or meaning that we'll construct the Sarkisov link for each of the families. So I have a table here. So what this Sarkisov link will look like is starting from our variety X. So first, we'll have this distinguished point, this CAN point there. We'll construct a divisorial contraction where the center is this CAN point, meaning we'll do a blow up of this singular point. It's not, so the blow up ideal is not the ideal of the point, but some non-reduced ideal, meaning we'll do a weighted blow up of the CAN point. And yeah, after this divisorial contraction, there will be some flops and flips. That means in this diagram from y0 to y2, we contract some curves, we extract some curves, but we don't do anything on divisor level. So these are also called pseudo-isomorphisms sometimes. And then this Sarkisov link ends with a Mori fibration to Z. Or, yeah, it's either a fibration or y2 is a, yeah, or it's a divisorial contraction from y2 to Z. So, yeah, I'll describe the table a bit that I get. But if we start with a CA4 singularity, we'll get into a complete intersection of pi degree 5, 6 in the weighted projective space 1, 1, 1, 2, 3, 4. And this Z has a quotient singularity of a particular type, 1/4, 1, 1, 3. If our Sextic double solid has a CA5 singularity, we get into another Sextic double solid with a CA5 singularity. And if we start with a general one, then we can show that we get into a different Sextic double solid. And so on. So we see that there's not we don't really see a pattern in these. To me, it looks like a completely random list of varieties that we get in the end. That meaning that this birational geometry changes very much when we put a different singularity. Yeah. In the CA7 case, we have these three families that contain Mori fiber spaces, and they also have different varieties in the end. Okay. So the main new point that I did was putting these CA endpoints on the Sextic double solid. The method I used works everywhere. And the second main thing, what I did was construct this divisorial contraction. So before, when people have needed to construct these divisorial contractions, either to singular points or smooth points, it's been relatively easier. But in this case, it's turned out to be very difficult. So I'll give some definitions, and I'll be very careful about the definitions because it's very, yeah, in my case, you need to be careful here. So I'll start by saying that if we have two birational morphisms from y to x and from y prime to x prime, we say that they are equivalent if we have isomorphisms to make this diagram commute. So this is a very natural definition. We say that they are locally equivalent if around the centers of these morphisms, birational morphisms, we find some open subsets such that these two birational morphisms are equivalent. And similarly for complex spaces. So this is to study the divisorial contraction or the blow up around the center and around the exceptional divisor. I'll discuss what the weighted blow up is. So there's many different definitions in the literature. And yeah, I'll show one. So we choose positive integer weights for the variables. I'll call them W1 up to Wn. And then this weighted blowup of affine n space, to construct this, we'll use a geometric quotient. So we know how to construct projective space out of affine space. You throw out the origin and you take a C star quotient. Here it's very similar. So to construct the weighted blowup, we take the affine space with n+1 variables. I'll add a variable which I call u, but I'll throw out this locus where all of the x1 up to xn are 0, and I'll take a C star quotient. This action that I have, C star action, is given by -1, W1, up to Wn. This means that lambda times u is lambda to the -1u, lambda times xi is lambda to the power of wi xi. And this construction really comes from toric geometry. This means that if we have a fan describing the affine space, so these are just the rays E1 up to En, then this weighted blowup is a weighted star subdivision of this span of affine space. So a usual star subdivision is if the weight vector is 1, 1, 1, 1, 1, and the usual star subdivision is a usual blowup, and this weighted star subdivision is a weighted blowup. So often, yeah. So yeah, this is the most standard definition. But we need to do the weighted blowups not for affine space, but for our sextic double solid. So if you have a subvariety of Cn, then we can take the restriction of this weighted blowup morphism. That means, yeah, you take the proper transform of the subvariety and you restrict the weighted blowup to the proper transform. But yeah, sextic double solids, these are not embedded inside affine space. So we need slightly more generally that the weighted blowup of some variety at some point is a birational morphism that is locally equivalent to the one given here from y prime to x prime. So yeah, you'll have a definition for affine space. For subvarieties of affine space, it's just a restriction, and in general, it's something that's locally equivalent to this. For a moment, I'll show the local equivalence again, which is just isomorphisms around the exceptional divisor and the center. Okay. Yeah, one comment that usually when people write about these weighted blowups, they just say it's, I don't know, let's say 112 blowup. But this weighted blowup actually really depends on this embedding that you choose. And if you change your embedding slightly, you get a different weighted blowup. And then there's a theorem by Kawakita. So this is what I use to construct these weighted blowups. I state it in a special case where n is at least 3. So if x has terminal singularities and has a CA endpoint at P, let phi be a birational morphism with center P, and phi is a divisorial contraction if and only if it's locally analytically equivalent to the R1, R2, A1 blowup of the zero set of F. So since there's a lot of words, so yeah, that a birational morphism is a weighted blowup if and only if it's local analytically equivalent to something, and we describe this something. So there's combinatorial conditions on the weights. Yeah, A divides R1 plus R2, and A is co-prime to both R1 and R2. N plus 1 is equal to R plus 1, R1 plus R2 over A. Then this third condition is a condition on the weight of F. That means if you write F as a sum of weighted homogeneous parts, then the least degree weighted homogeneous part has degree R1 plus R2. And the last condition is a specific form of this power series F. So x1, x2 plus h. So the way Kawakita wrote it, in, how it's written in his paper, the word local analytical equivalent is not mentioned. Yeah, because I guess in that paper they didn't apply it, but here I need to be very careful with the definition. And And the other point is here wrote it not weight of f is R1 plus 2, but weight of h is R1 plus R2, and didn't introduce f like this. It just wrote x1, x2 plus h immediately. So, but this is the same. So, but why I write this out, this f out explicitly, is that in fact in this Kawakitas theorem, so there's one condition that's redundant. We can't throw out any of the first three combinatorial conditions, but in fact the fourth one, we don't need this fourth condition. So having a very explicit definition of this local form is useful if you want to, let's say, prove that every such divisorial contraction has some property. But I look at it from a different point of view. I construct some map. I want to show it's this particular weighted blowup. And for this, I want to have as relaxed conditions as possible. So yeah, if we just remove this fourth condition to check that some map is this weighted blowup, we just check some combinatorial conditions. Okay. So, and this is here written out. So that right. So I'll use this theorem to show that it's a divisorial contraction if and only if it is weighted blowup. So yeah.
You want to show that it's a weighted blowup, satisfying these conditions, and then you conclude that it's a divisorial.
Yeah, exactly. That, yeah. I'll check these conditions for the map I construct, and then use this theorem to show it's a divisorial contraction. Yeah, so the first part of this proposition is that we don't need this fourth condition. And the second that I thought was interesting was that if we have two weighted blowups, and any two weighted blowups with the same weights will be locally analytically equivalent. Just to prove a bit more structure of these weighted blowups. And the main lemma I use is that two weighted blowups are analytically equivalent or locally analytically equivalent if we have a weight respecting biholomorphism or local biholomorphism. And what do we mean by weight respecting? That the weight of the jth coordinate of our map has weight at least the weight of the variable. So if we have variables xy up to xn and y1 up to ym, and a map psi from x to x prime, the weight of this coordinate psi I has to be, or psi, I call it psi j here, has to be at least wj prime. So this is a very simple definition of what are weight respecting maps, but in this generality it hasn't been written before, maybe because it hasn't been, people have not constructed these things globally, these divisorial contractions. Let's see. One point that I'll make is that I use local equivalence everywhere to check something is a divisorial contraction, like in Kawakitas theorem. But globally, two such blowups can be different. Okay. So I'll talk a bit about, let's see, 5 minutes left. I'll talk a bit how I construct these divisorial contractions, but this is a bit technical. So we have this form of the Sextic double solid. I'll write it minus w squared plus f6. And let's say with a CA4 singularity. And let's say we want to construct the 3, 2, 1, 1 blowup, weighted blowup. So we know that, so let's say if we just take in this weighted projective space, it's covered by affine patches, some of which are just the affine 4 space. If we take one of those and just choose weights 3, 2, 1, 1 for the variables and construct the weighted blowup, it will not be this particular weighted blowup described in Kawakitas theorem, that we have to give our equation minus w squared plus f6, we have to give this a particular form local analytically. So that's what we'll do. We'll construct a birational. We'll construct a local biholomorphism that gives it the form x1, x2 plus h. But this is something we've done before when we constructed this parameter space, so we know how to do this. So this is the analytic map. It's not so easy. And this gives it the specific local analytic form. But yeah, here the problem is I want to construct something algebraic globally, not something analytic. So given this local analytic map, what would you do to get something algebraic? Question for the audience. You have a local analytic map like that. How do you get an algebraic map out of that? It's two infinite sums. Change of coordinates. Well, yeah, change of coordinates, but one easy thing to do is just change the map, is throw out everything that's higher order. So we'll truncate these power series to polynomials, and then we'll have an algebraic map. And I'll truncate it, namely, to something very simple. I'll just take the degree 2 part from one of these. Then we'll globalize it for projective space, because above was for affine space. And after we truncate it like this, we'll see that the weight is 5 of our polynomial. And we use the proposition to get the divisorial contraction. So this is the most technical part of the paper, showing where to truncate exactly and how do we construct this. And the rest is following a known algorithm of constructing Sarkisov links. This is not, let's say, it's not my new contribution, this how to construct Sarkisov links. I just applied this known techniques to construct it in my case. Let's see. Yeah, this is a bit difficult to describe, but yeah. I guess I'll say that, yeah, if you first apply these algorithms naively, you'll get into trouble. And then you need to unproject, make it a bit different. So I'll show this diagram here. So how we'll do it is this map from x hat to x is this change of coordinates that we do, this global algebraic change of coordinates to x inside this weighted projective space with weights 1, 1, 1, 1, 3, 5. We'll construct this divisorial contraction, this 1, 1, 3, 2 blowup. We also do it on this ambient toric variety. And then we construct this link that means these flips and flops, and the divisorial contraction on this above ambient toric level, and we restrict it to our variety. And yeah, at first we're not lucky, and it doesn't restrict to a Sarkisov link. We change it a bit, and then we do get the Sarkisov link. And for the CA4 point, we'll get the Sarkisov link that Okada described in his paper. He started from this complete intersection and got the Sarkisov link to a CA sextic double solid with a CA4 singularity. The other Sarkisov links are all new. Okay. So this was the main part. I'll just say a few words here that people might want to know, that I started with CA4 singularities. What happens with the lower ones? The lower ones, we can run exactly the same methods, but we'll see that we don't get the Sarkisov link. We either get a diagram where at some point it leaves the Mori category. Yeah, we get the diagram where at some point it becomes non-terminal. It's like a link, but not the Sarkisov link. And we expect it to be rigid when n is less than 4. This is something I am working with Takuzo Okada, Igor Krylov, and Ji-Hoon Park. Okay, thank you.
Okay, is there a question? When?
It's a basic question. Why is it that finite dimensional what you wrote in the board?
Right. I'll stop the sharing. Let's see. Why is that finite dimensional? Right. So exactly, that's a very good point. That it's not always going to be finite dimensional. It's this is the bad one. Finite dimensional if and only if and only if the singularity is isolated. But this is a theorem. Yeah, in my case, I have these isolated CAN singularities.
Okay, is there any other question? If not, let's